What we're going to do right now is the E1 elimination of a tertiary alcohol. So I'm going to draw for us a tertiary alcohol. I'm going to draw it so that I can see bonds of interest. Okay. Now, if you're doing an E1 elimination with an alcohol, you have to have an oxyacid. The most commonly used one is sulfuric acid, but some others that are commonly used would be potassium hydrogen sulfate, which is KHSO4, or you could use something like nitric acid. The point is you would need to be using a very strong acid that contains oxygen. And you do this without water present because water is going to be one of the products. So this needs to be concentrated acid, and you are going to need to heat it up. Now, again, water is going to be one of the products, so we're trying to use Le Chatelier's principle here. If we are producing water, we don't want to have water in the reaction because we want to force the reaction to go towards the products. Now, I hope you remember previously that sulfuric acid is a very strong acid, and if you are not able to remember that, go back to your pKa table and you will notice that sulfuric acid is one of the strongest acids on that chart. It has a negative value. I can't remember its exact number at this moment in time. The point is, it is a very strong acid. And as a strong acid, it is going to be a source of a proton. One of these OH bonds is going to break. And oxygen, being the more electronegative atom, will take those electrons. So you've got a proton. That means you have to have a base present to pick it up. And a base must be an electron pair donor or a proton acceptor. The only atom that meets those conditions in this particular reaction is this oxygen. So it will pick up the proton and you'll make an alkyloxonium ion. And if you look at your pKa table, you will note that alkyloxonium ions, although they are very strong acids, are weaker acids than sulfuric acid. So this is favorable acid-base chemistry. And that's why this step proceeds, and it's a fast step in this reaction. The corresponding conjugate base in this reaction is hydrogen sulfate. Now, it again depends on the type of oxyacid you are using, what that conjugate base is going to be. But you definitely want it to be an oxyacid. And the reason for that is this anion has resonance delocalization of its negative charge. So I can draw, in this particular case, 3 different resonance structures showing the delocalization of that negative charge. Now, I know they look the same. That's the whole point. If these resonance structures did not look equivalent, I would have done something wrong. So I'm trying to draw all 3 of them for you. You only need to maybe draw one of them or just draw HSO4 minus off to the side. Okay, that would be sufficient for our purposes of a mechanism. But I just want to draw them out so that you are reminded that there is resonance delocalization of negative charge. Now, because there is this resonance delocalization of the negative charge in this conjugate base, it makes this hydrogen sulfate anion a pathetic nucleophile. It is a terrible electron donor. He's just happy to sit here. Each one of these oxygens has 1/3 of a negative charge, and as a result of that, they are terrible electron pair donors. Doesn't want to go anywhere or do anything. And that's the whole point of using an oxyacid. If you use something like HBr, which we have done previously with alcohols to show a substitution mechanism, the corresponding conjugate base in those types of reactions is the halide. And the halide is a good nucleophile. And then you would be doing a substitution reaction. We do not want to do a substitution reaction. Again, that is why we are using one of these strong oxyacids. We have to have a strong acid to protonate the alcohol. But we don't want the conjugate base to act as a nucleophile. That is why we are using the oxyacids, because their corresponding conjugate bases have resonance delocalization of this negative charge. Now, if you look at the oxyacid, you've got an oxygen here with a positive charge. Oxygen, I hope you remember, likes to be neutral or negative. And so it wants to get rid of this positive charge. It can do one of two things. You can break an OH bond, and if you do that, you go right back where you were previously. That is not productive chemistry. So the other option is to break the carbon-oxygen bond. And if that occurs, oxygen gets these electrons because oxygen is more electronegative. And the carbon just gets to deal with it and become a carbocation. So this is the slow step of the reaction. And as you can see, it only involves one chemical species. It has nothing to do with the conjugate base. That is why this is an E1. In the rate determining step, only one chemical species is involved. As a result of that bond breakage, I'm going to draw out this carbocation a little bit differently than what it looked like on the previous slide. But it's still the same thing. I'm just drawing out all of the hydrogens on the adjacent carbons to it. And you've also got water here. So you just kicked it off. Okay, so we've got a carbocation. Now, I hope you're seeing this looks very, very similar to the SN1 reaction of a tertiary alcohol with a hydrogen halide. It's the same first two steps. If you remember that SN1 mechanism, the next step was for the halide to add to the carbocation, and then you had the hydrogen halide. Again, we don't have a decent nucleophile. Our corresponding conjugate base has resonance delocalization of the negative charge. The only other potential nucleophile in the solution here is water. And water can act as an electron pair donor to this carbocation. It is absolutely possible. But if you do that, you go back to where you were a moment ago. And that's not productive chemistry. So we don't really want to see water acting as the nucleophile, but it can through equilibrium chemistry. The other option, instead of having water act as a nucleophile, is to have water act as a base. So not a Lewis base, but a Bronsted-Lowry base, and be a proton acceptor. And what it can do is remove one of these protons on one of these carbons that I'm going to show here in green that are adjacent to the carbocation. So I'm looking at the hydrogens on these adjacent carbons. Now if I do this, I would like to make the most stable alkene possible. So you want to follow Zaitsev's rule, which states that you remove the hydrogen from the carbon with the fewest number of hydrogens. So I'm going to do it from the carbon that has two hydrogens. I'm going to be able to make a more stable alkene by doing that. So water will come in here and remove this hydrogen. Out of carbon and hydrogen, carbon is more electronegative. So this carbon that I've shown here in green is going to get those extra electrons, and it will use them to make a double bond between these two carbons. That will be the major product of this reaction. It is possible, though, to make a minor product, and you could do that by removing one of the hydrogens on one of these primary carbons. So if I took one of these other hydrogens, which is possible, I could then take the carbon-hydrogen electrons and make the double bond here. So there are two products that are possible in this particular case. So I'm going to show the major product in red. Oops, that's be a CH3, sorry. That's the major. And the minor product would look like this. Now, the way I did this, there is no regiochemistry, or sorry, stereochemistry. These are regiochemistry. But what I mean by that is there isn't cis and trans with the reactions I chose. But be aware you may have more products if you have two different groups on one of those carbons. Like on the top one, you have 2 methyl groups on the right carbon, so there isn't any stereochemistry. And on the minor product, on the upper carbon, you have 2 hydrogens, so there isn't any stereochemistry. But you may potentially have stereochemistry, so be aware of that. But the point is, from this reaction, you are making a double bond. The other product of this reaction would be H3O plus and HSO4 minus. So it is acid catalyzed because the acid catalyst is regenerated. And you've pulled water off if you look at this. You could give the proton away from the H3O plus to the H2SO4. You are generating water as a product. That's what's driving this reaction forward. So you'd want to start out with the concentrated sulfuric acid. And the major product is the major product because it's a tri-substituted alkene. The minor product is the minor product because it is a gem disubstituted alkene. And if you remember from class, the more substituted the double bond is, the more stable it is. And that's why the product that you see there in red is the major product.